A quantum leap is the very smallest leap possible in nature, but it's proven to be an enormous step in thought. Subatomic particles, like electrons, are able to move from one point to another without ever occupying any of the space in between. An impossibility in our everyday world, but commonplace in the realm of the atom. In the subatomic world, atoms and their constituent parts play by a completely different set of rules from larger bodies of matter. A German scientist named Max Planck described these new rules in what he called quantum theory. And it's our next great discovery.
The quantum theory emerges around 1900 because there was a crisis in physics of monumental proportions.
A crisis.
A crisis. New phenomena were being discovered that violated Newton's laws. Madame Curie, for example, refined something called radium. Radium had this magical property of glowing in the dark. Energy was coming out of nothing. Particles were coming out of nothing. That violated the conservation of energy. Energy was coming from nowhere. Around 1900, people thought that energy was continuous, that you could cut electricity, magnetism, you can cut it into finer pieces without end. And yet around 1900, Max Planck, the great physicist, had the audacity to say that energy occurs in packets called quanta.
Now, why did he say that?
Because if you assume that light comes in these packets, then you could explain all the different kinds of phenomena that we were seeing, that at the fundamental level, at the level of the atom, there was a quantum effect, that energy was occurring in packets. This also meant, by the way, that matter has wave-like properties.
And this is what we call quantum mechanics?
That's right. Now, that's not the way the universe was supposed to be constructed. The atom was like a bowling ball. How can a bowling ball have wave-like properties? Well, in 1925, Erwin Schrödinger, an Austrian physicist, finally writes down the wave equation governing the electron. This is one of the greatest achievements of the human intellect. All of a sudden, we can now peer into the atom itself.
And so we're talking about atoms are waves, atoms are particles, but there's an uncertainty associated with them, right?
That's right. Then a few years later, Max Born, a colleague of Albert Einstein, made the fateful step. The question was, if matter is a wave, then what is waving? Max Born said, what is waving is the probability of locating it at any given point. We sometimes give our graduate students the problem. Calculate the probability that you will dissolve and you will rematerialize on the other side of a brick wall. Now that's absurd. How can you wake up in the morning and wind up on Mars? How can you go to bed and wind up on Jupiter? That's crazy. And yet you can calculate the probability of that happening.
It's probably low.
It's very low. You would have to wait longer than the lifetime of the universe. But for electrons, it happens all the time. That's what we call electronics. All the modern marvels of the electronic age and laser beams and microchips ultimately come down to the fact that electrons, you don't know where they are, they can be two places at the same time. How can that be? Two places at the same time. Because you don't know where objects really are. This caused so much problems that even Einstein finally broke with the quantum theory. And he said that I cannot believe that God plays dice with the universe.
With all of its weirdness and built-in uncertainty, quantum theory remains the best model of the subatomic world we have.